Thank you for the kind introduction. Today I will introduce the MetaWave perspective on electrification and advances heat for energy-intensive industries, focusing on how pilot-level technology can support a broader toward the low-carbon industrial heat. The main idea behind this presentation is that decarbonizing industry is not only a matter of replacing fossil fuel with electricity, as we have already said, but it also means redesign the way it is generated, transferred, controlled, and recovered inside the industrial real processes. The energy-intensive process industry still rely on high-temperature heat. This heat is often generated using fossil fuel, and it represents one of the most difficult parts of industry of decarbonizing. Within MetaWave, we address this challenge through three different sectors, as you already said, that is ceramic, asphalt, and aluminum. These sectors are different, but they share the common need, that is, require intense reliability and well-controlled heat. The project ambition is to reduce up to 30% of overall energy consumption and 95,000 of kiloton avoid of CO2 emission. However, the challenge is not only simple to replace a flame with electric source. The real change is rethink the process itself, where the heat is generated, how it is interact with the material, and how it are recovered and controlled. The main the industrial heat is difficult to electrify for three main reasons. The first, many processes require very high temperature. Clean, dryer, oven, and furnaces cannot simply be replaced by standard electric heater without consider the thermal profile and the process dynamic. The second, the material themselves impose constraint. They may have low thermal conductivity, may change their property during heating, or they may be sensitive to thermal gradient. This means that the quality of the final product strongly depends on how heat is delivered. The last, but not the least, the technology must be integrated into existing industrial system. It has to work with production schedule, energy cost, renewable electricity availability, safety requirement, and existing equipment. For this reason, advanced electric heating can decarbonize to abate industrial heat only when it is designed around a specific sector, material, and process. MetaWave focus on three sectors. In ceramic, the key challenge is the replacement of fossil fuel clean while preserving product quality, thermal profile, and industrial throughput. In this case, microwave plasma sources are considered a possible route to replace gas burners. In the second, asphalt production, the process requires heating and drying mineral aggregate and recycled asphalt. Moisture removal and the use of recycled asphalt pavement are the central aspect. In this case, direct microwave heating can support more efficiency the processing and enable a higher use of recycled asphalt. The last, in aluminum, the focus is on carbon anode baking. As we know, this is a long energy-intensive process where the temperature gradient and atmosphere control are critical. In this case, the combination between microwave and induction heating can help to control the evolution of anode during the treatment. So the question is not whether the sector need heat, because they clearly do. The question is how this heat can be provided with a much lower fossil carbon intensity. Thus, the transition is based not only on a single solution, but is a toolbox of solution. Today, many projects are based on fossil fuel and not gas. The transition involves electric generation, heat recovery, and digital control. The target is low carbon industrial heat that is efficient, controllable, compatible with industrial production. One important change is that the heat can be generated closer to the material or even inside the material, rather being only be transferred from the external flame to the material. This change the way we design the process. Thermal gradient, atmosphere, holding time, and material response are key variables. At the same time, electric heating opens the possibility of coordinating operation with electricity price and renewable energy availability. In MetaWave, advanced electric heating is considered a toolbox, as we have already said. In this case, microwave heating enables selective and volumetric heating. This can be useful when internally generation reduce gradient or accelerate the process. Plasma heating provides high-temperature electric heat and can replace combustion-based heat delivered in selected clean or furnaces environment. Induction heating is efficient only for conducting material, but especially when electric properties evolving during the treatment. Eventually, the hybrid system combines different heating processes to balance efficiency, uniformity, quality, and throughput. But technology alone is not enough. Industrial readiness also requires modeling, heat recovery, robust sensor, safety strategy, and flexible evolution. In our case, for ceramic, the transition from fossil fire clean towards high temperature electric heat for firing process. For asphalt, from flame-based aggregate heating towards lower carbon heating, in particular towards recycled asphalt use. For aluminium, the transition is from long collective baking cycle towards more controlled heat treatment. The main idea and the aim of this overview is to show that each sector requires a different technology route, that is plasma, microwave, and so on, induction. But the overall direction is the same: reduction fossil fuel use, improving energy efficiency, and maintaining industrial performances. At the project level, MetaWave aims to achieve a heating efficiency between 70 and 19%. This corresponds to 420 gigawatt per hours and more than 95,000 tons of CO2 emission avoided. The first estimation from representative industrial environment are already encouragement. For ceramic, the estimated reduction is about 30.5%. For asphalt, the estimated reduction is about 50.5%, with the additional benefit of enabling the use of recycled asphalt pavement. For aluminum, the estimated reduction is about 52.8%. Assuming post-combustion of volatile or energy recovery. This value should be represented as early estimated, not a final certificated performances. However, they already show the potential of process-specific electricity heating to support a credible transition in energy-intensive industries. Thus, to conclude, MetaWave demonstrates that industrial decarbonization requires more than electrification alone. It requires technology designed around real material, real process, and real industries construction. Thank you very much.